which is way, way, way faster than either of those two. One thing that we didn't put in explicitly here, right, but that it's important to keep in mind, is that all of the constants in these rates, they depend on the condition number of, say, the Hessian of the function. So they actually, they can be, the constants can be quite bad. They can make these rates look a lot worse if the function's poorly conditioned. Right? So even though we could be in a strongly convex situation, we may not see a rate that looks that fast just because of the conditioning affecting the rate. Okay, now let's look at subgradient descent. And just interrupt any time if you have questions. Yeah, Dallas.
Can we discuss how to actually compute projection onto a constraint set? Is that just a separate optimization
problem? So we did not discuss, say, in generic detail how to compute a projection onto a constraint set. If you look at a generic set, that is, you're right, another optimization problem. But we did talk about several special cases of constraint sets that we can project onto either in closed form or with efficient algorithms. And we had a list in, if you go back to the proximal gradient descent lecture where we actually introduced the projected gradient method, there's a list there of maybe like 6 forms of constraint sets that we can project onto easily. For example, a linear constraint is very easy to project onto. Right? There's a closed form operation for that. It reduces to solving a linear system, essentially. Some easy things like some easy cones are easy to project onto. Like, for example, the non-negative orthants are very easy to project onto. A box is easy to project onto. The L1 ball is easy to project onto. The L2 ball. So there are definitely some classes of objects that we know how to do, either with efficient techniques or in closed form. But if you write down a generic set, you're right, that's its own optimization problem. Good question. Other questions? Okay, how about subgradient method? That was the next thing that we looked at, right? And the reason we liked the subgradient method was really that there's no restrictions on the criterion aside from it being convex. There's no smoothness restriction. There's no kind of simple restriction like we had for proximal gradient for the non-smooth part. If we can compute subgradients of a function, then we can use the subgradient method. That's really all we need. How do we handle constraints in the subgradient method? Again, we project onto the constraint set. That's it's the same notion as we had in gradient descent. We take a step according to a subgradient now instead of a gradient, and then to get back into the feasible region, we project onto the constraint set. What are the optimization parameters we need? Well, there's the step size, right? There's one parameter that we have to worry about when we run the subgradient method. That's the step size. And we choose them to be diminishing, typically, in subgradient method. We could choose them to be fixed, right? But we saw in subgradient method, if they're fixed, then we don't necessarily have a convergent algorithm, right? We have a bound on how suboptimal kind of the resulting iterate is going to be after infinitely many iterations, but it's not going to be optimal unless we take diminishing step sizes, right? So a typical choice is, for example, something like 1 over k, where k is the step that you're at, something like that. What's the iteration cost for the subgradient method? It's cheap as well. We only have to compute subgradients and then add that to the iterate that we're currently looking at. So very cheap iterations with both the gradient method and the subgradient method. And the rate is actually, we saw it's quite a bit slower than the rate of the gradient method. Not surprising because we're not assuming any smoothness condition. The rate is 1 over epsilon squared. Right? So again, that can be a big difference for a small value of epsilon between 1 over epsilon squared and 1 over epsilon. Could mean a lot more iterations. Right? So what we gain is generality. We can minimize any convex function as long as we can compute subgradients. What we lose is efficiency in terms of the iteration complexity, number of iterations needed to get to an epsilon accurate solution. The next thing we looked at was proximal gradient. So that's what are the requirements for the criterion functions we're looking at. It's smooth plus simple. Right? So we needed to have f being g plus h, where g is differentiable. H can be non-differentiable, but we have to know the prox operator of h. Right? Remember what the prox operator was? It was defined in terms of its own minimization problem, essentially a least squares term plus h. We have to know what the solution to that problem is. So as long as we can evaluate that operator associated with h, we can use proximal gradient. We call those functions simple just because, for lack of a better word, that's how we'll refer to them. How do we handle constraints in the proximal gradient method? We didn't talk about this actually, but from what we learned in class, you could figure out how to do it. And there was a Piazza post asking this question as well, I think a few days ago. How do we handle constraints in the proximal gradient method? I want to write in the document camera for this, but I can't get it up. Just switch to this one? Yeah. All right. Okay, so let's just, for now, switch to this so I can write. So let's suppose we have, we want to minimize, let's say, over all x in some constraint set C. Some function which looks like g of x plus h of x, right? Where this is our smooth part and this is our non-smooth part. So how do we do that with proximal gradient? What do you guys think is our next step? We've seen how to lift constraints into the criterion before. We want to somehow, yeah, Logan.
So with the indicator of P and C is going to touch that on the H.
Exactly. So we're going to write up here, write the indicator function that x is in C. This will be infinity when x is outside of C and 0 otherwise. So it has the same effect as the constraint minimization problem, right? And now we're just going to call this our new non-smooth function, h tilde of x. So how do we use proximal gradient here? Well, we just proceed as before. Pretend like this is the non-smooth part. So we have to know what the proximal operator of h tilde is now, right at a point t. That's going to be the argmin over all z, 1 over 2t x minus z squared plus h tilde of z. Just by definition. And now if we wanted to be more transparent, we can also remember that h tilde was the h plus the sum of the indicator. So we could actually write that back in its constrained form, just if we wanted to be really transparent. Like this. Okay, so what is this? This is actually, it's a prox operator. But the reason I wrote on the slide, I wrote constrained prox operator. You can see the constraints now basically get carried into the prox. So if we can evaluate this, we can solve this minimization problem, then we can proceed as before, and our iterations look like this, right? The next update looks like we take the prox according to, this time, h tilde at the parameter value t, of the gradient step that we would have taken with respect to g. Okay, so that's how we do constraints with proximal gradient descent. So if I know the prox operator of h, am I automatically going to know the constrained prox? What do you guys think? Yes or no? So if you think about some of the prox operators, we know, like suppose h was the L1 norm, what's the prox then? The prox is soft thresholding, right? That's something we've seen a bunch of times. If we put a constraint here, it's not so easy, depending on what the constraint is. So actually putting in a constraint could either cause no problems, because maybe there's a very simple fix we need to do to the prox to get the constraint prox. Like for example, if we had the L1 norm, and I put in the constraint, if C was the non-negative orthant, if C said that all the components of Z had to be non-negative, then that's a very easy adaptation from soft thresholding to like a one-sided version of soft thresholding. Basically, if anything's negative, we move it to 0. Otherwise, we soft threshold as usual. But if I change that to something else, say some polyhedron or something, this becomes very difficult in general to go from a prox to a constrained prox. So it can be, even though in principle we could do it, it can become quite difficult to evaluate the prox in closed form with a constraint. So you might have to do something iterative here, right? Like approximately minimize this prox by running another inner loop for an optimization technique. Okay, and then something to mention that's quite recent is people have started looking at when does the prox decompose? Like when can I apply the prox of h and then basically a projection in this case? Or what, if I had h plus another function, when can I apply the prox of h and then the prox of my other function called h prime? When is that kind of approximation to the real prox operator going to work? And so you can take a look at some of the recent papers in NIPS from not this year but the year before. There's a few papers by actually a postdoc here in ML, a few nice papers about when the prox operator can either explicitly decompose across two functions or when we can kind of approximate it by decomposing it. So there is some room to budge there even if we can't solve the constrained prox exactly. All right, so that was how we incorporate constraints into a proximal gradient descent. Next consideration is the step size. What kind of optimization parameters are there? Well, there's the step size t, and it's exactly the same difficulty as gradient descent. Really no more. Either fix it or use line search. What's the iteration cost? Again, this is where it gets not so. We don't have a uniform answer for what the iteration cost is going to look like for a lot of these methods coming up because they're very different depending on what function we're minimizing. But I would summarize it by saying that it's moderately cheap. Right? We tend to use proximal gradient descent for problems in which the prox is moderately cheap. Right? Like soft thresholding, we can do in order n if it's a length n input. In that case, it's very cheap. In general, the prox we typically don't solve problems where the prox is very, very difficult to evaluate. Kind of defeats the purpose of proximal gradient descent. And the rate is the same as gradient descent, essentially, under the assumption that the smooth part has a Lipschitz gradient and the non-smooth part has a prox we can evaluate. Right? But each iteration here, right, is one evaluation of the prox, so just keep that in mind. Why wouldn't we solve problems with proximal gradient where the prox is really, really difficult? Right? Why would we not prefer that? I said that would kind of defeat the purpose, but why do you think that's the case? What's that? Yeah, that's not a bad answer, yeah. Think about comparing to other methods where the iteration cost is expensive. Right? For example, the fourth column on this list. So not that they necessarily have the same scope in terms of what problems they solve, but you can think about for the expensive methods, say Newton's method and the interior point methods, we are willing to essentially encounter or willing to pay for an expensive iteration because the number of iterations required is very small. They converge very quickly when they're in the right neighborhood. Proximal gradient doesn't have that advantage. Right? It converges the same rate as gradient descent. So it would not really make sense to use proximal gradient for a problem where the iteration cost was really expensive, where the proximal operator is really expensive, because we need a lot of iterations to get somewhere. And we're willing to essentially pay the price of an expensive iteration in Newton's method or in the barrier method or in the primal dual interior point methods because they have such fast conversions. So that brings us to Newton, which is the fourth column. What are the requirements for Newton's methods? Doubly smooth functions, right? We need the gradient and the Hessian in order to use Newton's method. What kind of constraints can we handle? We can handle equality constraints with Newton's method, as we've learned it. And how do we handle equality constraints? Right, we have a way of basically solving a bigger linear system in order to make a Newton step that preserves the equality constraint. We called that, I think, that bigger matrix we sometimes call the KKT matrix. We saw how to do that with Newton. What are the optimization parameters? Again, it's just the step size, and we can take it to be fixed, in which case we typically choose it to be 1. That's the pure Newton's method. But that may not converge in general. So, the safest route, the most common route in practice, is to use line search. backtracking, just like every other instance of backtracking we've learned, it's the same formulation. If you look back at the slides, they're really all unified in a sense. All they differ in is the update direction. That's the only difference between the formulations of backtracking. What's the iteration cost for Newton's method? Again, we might summarize it as moderate to expensive. Right? We have to compute the Hessian. We have to solve a linear system. We learned from our numerical linear algebra primer that could be on the order of n cubed, right, in the worst case, for a dense Hessian, for an n-dimensional problem. Right? Compare that to computing a gradient or evaluating a prox. Those are typically way cheaper than n cubed, typically on the order of n. For structured Hessians, this could be a lot cheaper, and then we like to use Newton's method in those problems. Like, for example, for a banded Hessian or a sparse Hessian, it can be closer to n than n cubed in terms of number of operations. What's the convergence rate of Newton's method? We saw that it was log of 1 over epsilon. Right? That's called a quadratic rate. It's way faster than anything that we've seen up to Newton's method. It's, again, one way to remember this is that it's like 5. Right? Because if epsilon is like 2 to the minus 32, then log of 1 over epsilon is 5. And 2 to the minus 32 is pretty small. You might not ask for anything smaller than that in practice in terms of the distance to optimality. But it's important to remember this is a local quadratic convergence rate, which means that what we proved, if you look back, or we didn't actually prove it, but what the notes outline in a proof that we didn't really go through, is that if we're in a region, kind of a basin of attraction of the optimum, then we get this very fast convergence rate once we enter that region. Okay, so it's log 1 over epsilon once we're kind of close enough to the optimum. If you ask for its global convergence rate, then I believe it's linear, log of 1 over epsilon. But we typically think of Newton's method as, being able to get into this what we call the quadratic convergence regime quickly, and then basically it can solve the problem up to as high a degree of accuracy as you'd like. Quasi-Newton is an interesting kind of cousin of the Newton method. We didn't talk about it in detail, but I wanted to put on the slide because it's something that people, at one point at least, used a lot in practice, and I think still it's used in certain problems. And it's essentially is the same as the Newton method in many regards, except for it doesn't exactly solve a linear system in the Hessian. It approximates the Hessian with a sum of kind of low-rank matrices, and it solves that system instead. And so for that reason, its iteration cost is typically cheaper than Newton's method, and can be a lot cheaper if the Hessian is dense, for example. Because the Hessian that we construct, this approximate Hessian, it comes from just gradient evaluations. What's the rate of quasi-Newton method? Maybe there's not a super precise statement that I can make from our notes, but a summary is that it's super linear. So it's somewhere in between linear and quadratic. So it's not quite as fast as Newton's method, but it's also faster than a linear rate. And you can think of it like n steps of the quasi-Newton method basically can be equated with one step of Newton's method. So as an n-step quadratic rate. Any questions about this slide? This is, the core of the stuff we learned. The first three are first-order methods. This is our canonical second-order method. Quasi-Newton is an interesting cousin of Newton. The next slide has some of the stuff we covered more recently, like the Berry method and the interior point methods. But this formed at least the heart of the first part of the class. Yeah?
So gradient and subgradient, when we do projection to satisfy the constraint, do we get the same rate of convergence?
Yes.
Yeah.
Uh-huh. It's the same rate, but remember now one iteration does a gradient or subgradient update and a projection. So if that projection is expensive, then that may be misleading. But it's the same rate. Good question. Okay, let's move on. Oh, Yusheng, yeah.
Just trying to, I just want to point out that there are also other methods like stochastic gradient or coordinate descent methods that you can also put into the chart yourself, and they typically have the same rate of convergence as first order methods.
Yeah, that's a very good point. So actually, we have coordinate descent on the next slide. There, you could put many other things on this table. And the next slide has a few, but Yusheng also raised a very good point there, which is that the constants here, we've hidden them, right? And they typically depend on the problem size, n. So actually, maybe a more refined analysis, which you'll see maybe in a more advanced course, it pays attention to the constants and how they scale with n, and you can see that actually that can make a very big difference as well. Not just the complexity in terms of epsilon. Okay. So let's go through the first two columns. The next two columns I'm going to leave until we actually cover them, but I wanted to put them on here for completeness, because they're two very common methods outside of the ones we learned that we'll cover as well. So there's the barrier method and the primal dual interior point method, and that's essentially a recap of all the algorithms we've learned so far. The barrier method applies to doubly smooth criterion functions, just like Newton's method. And the constraints, now we think of them as constraint functions, hi of x less than or equal to 0. And as long as those functions themselves are doubly smooth, we can handle any set of inequality constraints with the barrier method. Okay, it's because we kind of lift those into the criterion with a log barrier function. We can handle equality constraints as well, right? Just basically the same way that equality constrained Newton worked. What are the optimization parameters for the barrier method? Well, there's two loops in the barrier method, right? Remember, there's the inner loop, which is that once we've lifted the constraints up into the criterion, we have to actually solve that smooth problem, say, with Newton's method. And that inner loop requires choosing a step size. Right? So we can do that, say, by a backtracking line search. That's typically the most common way to do it. The outer loop then changes the barrier parameter at each iteration. Right? The barrier parameter is what multiplies the criterion, or say the barrier term, depending on how you parameterize it. Initially, we learned it as if the barrier parameter was multiplying the criterion. So in that case, you want to make the barrier parameter larger and larger in every outer loop, so that the smooth constraints have less and less effect, right? And they become kind of more like hard constraints. So you have to have some parameter that tells you how you're going to update that barrier parameter, how it's going to diverge. And that's another parameter you choose for the outer loop. Maybe like 10. You're going to multiply the barrier parameter by 10 at each outer loop. The iteration cost of the barrier method, I would summarize, again, this is, it's hard to make these more concrete than what we have, as expensive to very expensive, right? Because each loop then has an inner loop which solves a problem using Newton's method. So every iteration is a full solve with Newton's method. So the outer loop, if we're thinking of that as the iteration, expensive to very expensive is the summary. What's the rate? It gets a linear rate of conversions in summary. So log of 1 over epsilon iterations gets us to an epsilon accurate solution. Now that's true both in terms of the number of iterations and the number of Newton steps. If we also asked to consider each iteration in the inner loop as an iteration, it would also be true that kind of under enough conditions about how we choose the parameters and the conditions on the criterion function, we can think of the number of Newton steps required as log of 1 over epsilon as well. Okay, because basically we can just use a constant number of iterations in each inner loop to get a solution of the desired accuracy. Okay, so I think barrier method was kind of an easy to understand conceptual extension of Newton's method where we actually incorporate constraints by putting them into the criterion. Then there's the primal dual interior point methods, which Javier covered last week. And their summary is similar to the barrier method. So in a sense, the distinctions between the barrier method and the interior point methods, they're not really fully described between these two columns, but you should remember the distinctions that we learned all throughout the last week of lectures. The criterion function that a primal dual interior point method uses is one that's doubly smooth as well, and that we can use doubly smooth constraints as well. So in that sense, they're similar. With the primal dual interior point method, there's no notion of outer and inner loops. Remember, it was just essentially one Newton step we perform, and then we update the barrier parameter. So there's no notion of outer and inner loops anymore. There's just one kind of grand loop. And for that, we need to choose a step size, say, by line search. And we need to figure out a scheme for updating the barrier parameter as well. So it's the same kind of idea in terms of the optimization parameters. The iteration costs, though, right, because there's no outer loop, we're thinking of iterations as just a single Newton step each time. We might categorize them as moderate to expensive, because one iteration is one Newton step, so it's essentially one solvable linear system. That linear system in the primal dual interior point method, as we learned, can be quite large. Right? So it can be quite a large linear system that we need to solve. And the rate is still log of 1 over epsilon, in terms of the number of iterations required to get an epsilon accurate solution. All right, so these are the algorithms that we've learned so far. It's good to keep them all in mind. You can even print this out and post it on the wall next to your desk, for future days when you're thinking about what algorithms to choose. I think this table also summarizes the fact that there's not one answer, right, when you're solving an optimization problem as to what algorithm you should use. Right? It depends on the problem. It depends on all the kind of aspects of the problem. It depends on how sophisticated you want to make your implementation in terms of the number of parameters you need to figure out. It depends on whether or not you have memory restrictions. It depends on whether you want a very accurate solution or just kind of a roughly accurate solution. It depends on a lot of stuff. So summaries like this are helpful because you can remember kind of the strengths and weaknesses associated with each method. We'll learn both ADMM and coordinate descent in the advanced segment of this class. And I'll just point out one nice thing about coordinate descent, this last method. There are no optimization parameters. Okay, so there are none whatsoever. There's no notion of a step size, nothing like that. So that's one reason why you might like using coordinate descent in an application, because you don't have to worry about whether or not you have kind of the right step size for your problem or the right, if you're using the interior point method, the right way to diverge the barrier parameter, etc. So one of the few methods that we know of that doesn't have an optimization parameter. It's also not as widely applicable as the interior point methods, right, which is why I can get away with that. Any questions? Yeah, Dallas.
I think the barrier method doesn't require doubly smooth unless you want to use of the interior. Is that correct?
Yeah, I suppose so. This was also a question that Jersey asked, I think, during the barrier method lecture, which is why do we use Newton's method in the inner loop? Why don't we use something else? And my answer was that, the lecture I gave wasn't super precise about how close we need to stay to the central path. I just kind of said that if we could stay in the central path exactly, it would take us this many steps. But as Javier made kind of clear in his lectures, there's really a neighborhood of the central path you have to respect. And if you use a method like gradient descent or something for the inner loops, then it would require an enormous number of iterations to get usually the accuracy required to stay in the neighborhood. We use Newton's method because, especially in the kind of locally convergent, quadratically convergent phase, it can get us very close to the central path in very few steps. Yeah.
So you said that our choice for which algorithm to use will depend on whether we want a very precise solution or just an approximate solution. It's not clear to me if I want an approximate solution, what would be preferred?
Well, I mean, we're going to spend 2 lectures after the midterm on case studies. So I'm going to go through 2 classes of problems, and I'm going to talk about different situations you might be in, and then we'll kind of detail what algorithms you might use when. So you'll get an idea of that then. But let's just do a quick thought experiment. Let's suppose you had a huge problem, right? Absolutely enormous problem, and you wanted to, suppose it's even smooth. The criterion function was smooth. You had a huge problem, and I told you wanted just kind of something that was close to a solution, because I'm not going to actually use that for a statistical purpose. I'll use it downstream for something else, and I don't need a very accurate solution. Well, if the subgradient method, right, or the gradient method in this case, can get us, something that's even roughly close to the optimum in a number of iterations that's reasonable, and each iteration is cheap, then we might use that instead of Newton's method, right? Because Newton's method, if n is huge, n cubed is enormous, And the strength of Newton's method is that when it's in the right phase, it gets us a very accurate solution, but we don't care about that now. So we might just expend, say, 10,000 iterations of gradient method or stochastic gradient, and as long as we're kind of close to a solution, we'll be okay. And like I said, we'll do a few case studies the next couple lectures where you can see maybe where you might want to use one method over another. So it's good to keep this table in mind for them as well. Any other questions? Okay, let's take a few-minute break, and then when we come back, I'll just take open questions about the course, or you can ask me questions about the midterm practice. Half an hour, maybe close to that. If there are no questions, we can all go home and study for the midterm. If there are questions, we can stay until 11:50. So whatever you guys want. So we can either do, like I said, we can go through some of the practice problems, or you can, if you have questions that are lingering from any of the homeworks or the lectures, that's fine too. So ask away. Number 6. Okay, so unfortunately I can't get both projectors up, so we're going to have to just stick with the pad, but that's fine. I'll write down the problem here. So the problem is to derive the dual of this problem. Minna for all x. Okay. So let's talk through this. What's the first thing you would do here? Right. So this is a problem without constraints. And what's the dual function for a problem without constraints? Strictly speaking, what's the dual function? It's a constant, right? It's well, first of all, there are no dual variables because there should be a dual variable associated with each constraint, but there are no dual variables, so the dual is a function of nothing, and it's given by the minimum over x of the Lagrangian. The Lagrangian is just this. There are no constraints to live up there, so the dual function is a constant, and it's equal to f star, the optimal criterion value. So that's not very useful. It's not a dual problem. So we learned that when you don't have constraints, what's the kind of trick that you do here? You introduce constraints, right? You make a substitution that doesn't have any effect on the problem, but that will allow you to derive a dual problem. So there are various things you could do here. Typically, one thing to keep in mind is that if you have a matrix, right, that's convolved, or not convolved, that's composed with a non-smooth function, then that can be quite difficult. Because we're going to eventually take, how do we think of duality? We think of it in terms of conjugates, basically. And we know conjugates of things like the L1 norm or other things that are simple, but once we stick a linear transformation in there, that can be quite difficult. So if we make a substitution, we want our substitution to kind of pull out the matrix, we think. Typically, that's a way to derive a dual. There are multiple ways to derive a dual here. They won't be the same dual, but they'll all be equivalent. So we're going to try this substitution. We're going to call that part zi in this case. You could have also called aix plus bi zi. That actually would have resulted in the exact same dual. It's really the difference in whether you call, say, this x z or whether you call aix zi. Okay? And so we're going to write the problem then in this form. Subject to ai x equals z for all I. Okay, so now we go through the regular steps for constructing a dual. we put this into the criterion. Okay, so the Lagrangian, now we're going to associate one dual variable with each of these constraints. Each of these constraints is actually, sorry, this should be zi, right? X and z, and all zi. Right, so the Lagrangian now is a function of our primal variables, x and zi, and also of dual variables, which we'll call ui. And right, we just have the criterion. Plus u transpose. And here I don't think it actually matters whether you write it as, and generically it doesn't matter whether you write it as zi minus ai x or the other way around. But when I worked out the solution to this earlier, I had it as zi minus ai x, so I might as well leave it that way. Okay. And now let's just rearrange basically so that we have terms that only involve say zi and only involve x. And sorry, we actually have, right, we have one dual variable for each constraint. And the Lagrangian involves all of them. So that's what the Lagrangian looks like. So let's just, like I said, rewrite this so we can separate all the terms involving zi and separate all the terms involving x. So all the terms involving zi, we can collect them like this. This is just ui transpose zi. And then all the terms involving x. So here's the thing to notice. The only thing that multiplies x is really a single vector, right? And that vector looks like this. Right? I just pulled out x from the sum, and I said that it's really just one vector multiplying x, sum of ai transpose ui. Okay? Now we can basically, we're going to minimize this part over zi, and we're going to minimize this part over x. That's our next step, because we've got to minimize the Lagrangian over the primal variables. And I wrote it this way so that we can separate out their roles. Okay, so let's do the minimum over x first. Part's easier. So what's the minimum over x? It's a quadratic, right? So we should, I don't remember what I told you to tattoo on your arm, but I thought it was either this or the least squares derivative. So you might as well get both tattoos. Right, the minimum of a quadratic is minus b over 2a. If the quadratic is ax squared plus bx plus c. And so what's the minimizer here? It's just going to be ai transpose ui summed up. It's the matrix version of what I said. Because right, this is just x transpose x times a half, and this is just, think of it as b transpose x. So it's essentially what the minimum over x is what we get when we plug in for x this value, the sum of ai transpose ui. And if we plug it in, you can see we get that value here squared. And there's a negative sign, and we get half that value here squared. So in total, it's just negative half that value squared. Okay? And how about the minimum over zi? Right? Well, this is almost, okay, so first of all, to minimize over all of z, we can minimize over each zi, right, because the way they separate out. That's why we wrote it like this. And so we're going to look at the, should try to emphasize that it's the inner term we're looking at for the minimum over zi. And it's almost like the, looks like something like the conjugate, involving the conjugate function of the L1 norm, right? But then there's this bi here that's a bit bothersome. So had we made a different substitution initially, there wouldn't have been a bi here, there would have been a bi somewhere else. But this also shouldn't bother you too much. You can see that the minimum of this whole thing over zi, right? Zi is just a variable name. Let's just call yi, make the substitution yi is equal to zi plus bi. So if I minimize over all zi unconstrained, I can also write it as a minimization over yi. That's fine. So it's going to be the same as the minimum over all yi of this term is just yi in the L1 norm. And this term is going to be ui transpose yi minus ui transpose bi. Right? After the substitution, I just turned this into this, the same problem. And now this doesn't involve yi, so this is just going to come out. Right? And what is this? Right? It's kind of, we know it's related to the conjugate function of the L1 norm. The conjugate function of the L1 norm would be the maximum of this minus that. Right? And so, and the conjugate function of the L1 norm is the indicator function that the whatever is multiplying the linear part is in the L infinity ball of radius 1. So, had we written that down on our midterm cheat sheet, which wouldn't have been a bad idea, it's not a bad idea to write down some of the common things we've seen in class involving the L1 norm, L infinity norm, those proxies, the conjugates, etc. We could have just read off that this is going to be minus the indicator, because instead of a max, right, we have a min. So I turned it into min of minus this quantity. And now instead of ui, I have minus ui. Infinity norm is less than or equal to 1. Right? But that's the same thing as the indicator that ui in the infinity norm is less than or equal to 1. Okay, so our dual problem is given by maximizing the dual function, which we get by minimizing the Lagrangian. So the dual problem we can now just write out from what we saw. It's maximum over all ui, those are our dual variables, of whatever's left over, right? So what's left over? We have these terms, ui transpose bi minus, because we have one for each zi in the minimization. And then we could write that as minus an indicator of, it should have been minus an indicator of this guy, but we can write that also as a constraint. So I wrote that up too high. We can just write that as a constraint rather than an indicator, subject to ui is less than or equal to 1 for all I. And then we have minus what we got from minimizing the part over x, which is just this. 1/2. No, sorry, the sum's on the inside of the norm. The norm of I transpose u squared. Questions about that? So another friendly suggestion is you should remember the relationship between conjugates and duality, because, well, there's two problems on practicing how to drive duals here. You can guess there's probably going to be one in the midterm. And look at the, make sure you understand this, and then go to the dual lecture or the dual lectures and remember the relationships between conjugates and duality, because that'll be very helpful. Yeah. Right.
So we could have done a similar thing here, right?
Yeah, you could have shortcut this. That's true. I just wanted to go through the steps to make it clear.
So in that case, I think we will be getting indicator functions in both f and g.
No, if g you take to be this guy, right, then...
I will be taking g
seeing these? Yeah, so I mean, in the homework, we had a sum of two functions. You'd want to maybe extend that result or make sure that result's true when you have a sum of many functions, but that's why I didn't do it here. But you know, the conjugate of this guy does not involve any indicators. It's not a norm, it's a norm squared. Right, that's why we saw that the conjugate ended up just being itself another norm squared. Remember, we learned that the conjugate of a quadratic of 1/2 x transpose qx was another quadratic in Q inverse. It was the L2 norm, you're right, it is. So L2 norm squared is a quadratic, and the conjugate is another quadratic. The L2 norm, its conjugate is the indicator, right, that the L2 norm is less than or equal to 1. Other questions? Number 9. Yes. Actually, let's not do 9 because I sent a Piazza post out saying you wouldn't have to worry about it. I'm happy to go through it in office hours, or you can ask me after class. But this involves like matrix derivatives, which we didn't really go through in class. There's just a little bit of trickery, basically, because one of the matrix derivatives is asymmetric. But don't worry about that for the midterm, but I'll be happy to do it like later or in office hours. Yeah, number 1. That's a good one to go through. Okay, so let's do problem 1. So problem 1 is to, it asks you to derive a dual of this problem. Minus 4y1 plus 2y2, subject to these conditions. Okay, so this is problem number 1. Has us derive the dual of this linear program. So as Justin noted, what's the constraint set here? Right. So if you add these two equations together, we get that the left-hand sides cancel, and we get 0 is bigger than or equal to 3. Right, so it can't happen. So what does that mean that the f star is, the primal criterion value is here? If we're minimizing something over an empty set of constraints, the criterion function is infinite, right? We take f star to be infinite. Minimum of something over no constraints, infinity. So the primal is infeasible. Its criterion value is infinite. So even before, right, so what we actually want to do is write on the dual of this, and then we want to figure out the duality gap. And we want to, specify the duality gap. So even before we go and compute the dual, the primal is infeasible, right? So what is the only way in which the duality gap can be non-zero for an LP? Think back to our very first duality lecture. We covered this. So for LPs, we get strong duality, right? Well, we can walk through it. We get strong duality when the Slater's condition holds, which means that in the primal, the constraint set is feasible. That's all we need. But we can also apply Slater's condition to the dual, and strong duality holds if the dual is feasible. So if either the primal is feasible or the dual is feasible, we get strong duality in an LP. So which means the duality gap is 0. If both the primal and the dual are infeasible, then the duality gap is infinite. right? Because the primal criterion value is infinity, the dual criterion value is minus infinity. So had we seen that this was a feasible constraint set, the answer would have been duality gap is 0 before even computing the dual. So no matter what you compute for the dual, you better get that the duality gap is 0. Now that we've seen that it's infeasible, the duality gap can be infinity, and it can be infinity if the dual is also infeasible. Okay, so it's just good to establish that in your mind before you compute the dual. So let's rewrite these three constraints in a trivial way, just to get them in line with how we want. You could go through this calculation in multiple ways, right? You can do this using the very first way that we learned for duality, which is you basically assign a multiplier to each of these, and you add the constraints together until you can get the criterion. That was the first way we learned how to compute duals. The second way was through the Lagrangian, which is more general, and I think is the one I tend to remember. But if you want to use the first way, that would be fine too, to get the same dual. And the third way is just to think about all of this as a general form LP, where this is C transpose Y. This is written as, I can write this as A times Y is bigger than or equal to B, and I can write this as Y bigger than or equal to 0, and I can just, if you've written down on your cheat sheet, what the dual is in terms of the transpose of A and B and C, etc., you can just plug that all in as well. I think that's probably more work than deriving the dual from first principles, but it's up to you. So let's just go through the most standard way, which is with the Lagrangian. So I'm going to rewrite all these constraints trivially. Okay? So nothing special there. And the Lagrangian now is, we'll use 4 Lagrange multipliers, U1, U2, U3, and U4. So it's a, it's a function of Y1 and Y2, and then U1 through U4, and it's just equal to the following plus U2 times minus Y1 plus Y2 plus 1 minus U3 Y1 minus U4 Y2. Okay, and now we want to minimize this over Y1 and Y2. Well, clearly, if it's a linear function, we minimize over like Y1. It's either going to be minus infinity or it's going to be 0. Right, it's going to be minus infinity if the coefficient that multiplies Y1 is non-zero. Otherwise, it's going to be 0. Same thing with Y2. So let's collect all the terms that multiply Y1. They look like Y1 times minus 4, and I have plus U1, and I have minus U2. And I have minus U3, right? Okay. And that's it. And then I have all the terms that multiply Y2. I get 2 minus Y2 plus Y2. Sorry, this is supposed to be U1 and U2. And I get minus U4. And then I have to remember that I had a few U's that were hanging around that didn't multiply any Y's, right, like this one, plus 2U1 and plus U2. Okay? So basically, in the dual, we have to have this and this equal to 0. Otherwise, the dual function is not defined. It's minus infinity. So the dual is to maximize 2U1 plus U2 subject to these two constraints. that these things are equal to 0, and also subject to the constraints that all the dual variables are non-negative. So to write out the dual, just to be explicit, the dual is maximize over all u1 through u4, 2u1 plus u2, subject to minus 4 plus u1 minus u2 minus u3 equals 0, and 2 minus u1 plus u2 minus u4 equals 0, and u1 through u4 being non-negative, right? And let's add these two together. Let's just check now if the dual is feasible. Let's add these two constraints together, and we get that minus 2 minus u3 minus u4 is 0. If we add these top two constraints together, which means that u3 plus u4 is minus 2. Which can't happen if u3 and u4 are both non-negative, so the dual is infeasible, which means that the duality gap is infinity. Ta-da! That was my QED sign. Yeah.
How do you design problem where both the prime one and the dual?
How do you design this problem?
Yeah, I mean, did you just play around any constant or?
This was from last year, and I can't remember how we did it last year. This was actually on the midterm from last year. And so was the one we just did, the dual problem with the AI, X, etc. I can't remember. I mean, it's difficult. They're really pathological examples where both the dual and the prime are infeasible. Typically, like I said, at least one is feasible. Yeah? So to minimize L, right, we go back to this part here. So we're minimizing L over y1 and y2. This always stays in the criterion, right? This gets put down. Let's suppose we minimize over y1, and this was non-zero. So let's suppose this value, was whatever, something. We'll call it A. If A is positive, I can always take y1 to be as big negative as I want and make this minus infinity. If A is negative, I can always take y1 to be as big positive as I want and make this minus infinity. So basically, this is minus infinity unless this whole term is 0. Minus 4 plus u1 minus u2 minus u3 is 0. So that's why we have a constraint here. It's really like we really had minus the indicator that this thing was 0. And I just put it into the constraint. It's the same thing with y2. I think we're at time. I hold office hours now. There's office hours from Mattia today, and I believe we're going to have 2 office hours tomorrow to help prepare for the midterm. Bring the midterm practice questions to office hours if you still have questions about them. Otherwise, we will see you Wednesday morning.